So, let's just say sorry to the other people who are watching the videos, because I forgot to record sound in the previous video. And now all you other guys who are watching are screwed. Whatever. The first part of the lecture wasn't that complicated and important. More important, because you've already heard of lists, all of you. So the more important part, stacks. What are stacks? Well, I mentioned what are abstract data types in the first part, so I'll mention it again quickly. A stack is basically some kind of array, and this array gives you access only to the elements at the top. Meaning, if you add elements, for example, add this element, then this element, then this element, and this element, add 4 elements. When you say, give me an element, it will give you this one over here. When you say remove an element, it will remove this element. And when you say give me again an element, it will give you the next. And the last element which comes in will be the first one which comes out. Again, abstract data types, basic definition of what their functionality should be. No restrictions on implementation, meaning that a stack might function as might contain an array, a list, or whatever. What's important is that its last element which comes in is the first one which comes out. Imagine a pile of dishes. As I said, after you wash a pile of dishes, you can't remove the bottom dish because everything will break, and you just remove the uppermost dish. So basically, when you add 3 dishes, the last one which you put on the top of the others will be the first one which you can take out or look at or whatever. So the method push means place something on the top of that stack. The method pop means remove the top element from the stack. And I think there's a peek method which tells you what is the top element. You can always look at the top plate in a stack of dishes, and you can always remove it, but you can't touch any of the other plates. You can't look at them, you can't remove them, you can't insert in the middle or whatever. So, this thing is useful practically everywhere, and that's why your programs, all of your programs, have an execution stack. What's the execution stack? Well, basically all the variable names and pointers and things like that are in this program stack. But that isn't important right now. What's important is what you can use them for, what you can use that stack. Well, you can use stacks in many ways, mainly in some graph traversing algorithms, but we'll start speaking about this right about now. So, again, various implementations. The same way in which we can implement a list, we can implement a stack, with the restriction that in a list we can access each and every element. In a stack we can address and access and do anything we want only with the top element, or the first element, or whatever you like to call it. It is usually called the top element and will be referred to as a top element. So, you can use the linked implementation, which means that you don't have a static piece of memory in which your elements are placed, like in the list. In the list you have an array with elements, and each element is after the next, in the normal list in C#. And each element is here and here and here and here, for example. In the linked list we said we have some elements connected with other elements, and these elements can be put in any way possible. So this thing is applicable to stacks also, because in a stack you have to actually store some memory, and this memory you don't know how large it will be, because the user can add, the programmer can add an infinite amount of elements until his RAM runs out. So you don't know how many elements there will be, so you can risk it and use an array which doesn't resize. You can use a linked representation, meaning the sort of linked list in which we said we have a value, some value, and a pointer to the next element, and these elements are randomly spread out in the memory, which is probably more effective in this situation because in a stack you won't have to access by index, you can only access the first one. And if you don't want to implement all of this by yourself, you can use the stack class in C#. And in every other major programming language, you will have a stack class implemented in some way. So, how you implement an array-based class? Well, you make an array, and you say the top element is the element at index, in this case 3, for example. And when you add elements, well, you write them here. For example, you add 5, and this top index goes over here. And when somebody says, give me the top index, give me the top element, it will give you 5. When someone says, remove the top element, well, we won't necessarily delete 5, you just have to move top 1 index back, for example, and make it point again to here. Yes?
Then you need double linked list.
When it's an array, you don't need linking.
Not array, double linked list.
Yeah, if you have a list, you need a doubly linked list. Exactly. But here we're talking about the array base just. So when we're talking about arrays, we have contiguous memory. Contiguous memory means what I said a little while ago. Each memory is after the last. When we have lists, we don't have that, but for now, we will just speak about the contiguous memory case. So yeah, we have contiguous memory here, meaning that every element is after the previous, or at the beginning, because there's no previous element before 0. So every element is after the previous, and if you represent a stack in this way with an array, we will just have an index to the top element, and you will put elements after the top. If, for example, if you add the element 5, the top index goes over here. Then you remove 5, meaning this thing leaves. There's still 5 here, for example. It's not necessary to delete it. And you have the top element pointing over here again, the top index. If you want to add an element, you add at the index top plus 1. Meaning you add here, and if you want to add 19, for example, it will overwrite 5. 19 will go over here at top plus 1, and this will become 19. And then top will go over here again. This won't be top anymore because we have another element at the next position. Top will be over here, and if you add another element, the other element at top plus 1, for example, will be 3. And top will go here, etc., etc., etc. Then over here, and things like that. How does this limit you? Well, when you reach the end of your array, you will have to resize. And if you add a lot of times, you will have to resize each time. And there's the choice, you can resize, you can double your capacity, for example, but that would be a list. So, as we said, the top index, this is an index, not a pointer, not anything else, an index. This thing moves left or right when you pop or push. So this thing was push, for example, 5. And top goes over here. Then push 13. And top goes over here. Then pop. And pop removes this thing and goes over here. Then push something else. Top goes over here again, and for example you push 19 and this thing becomes 19. So that's basically how you represent a stack with an array. How you represent a stack with a pointer, meaning how you represent a stack with a linked list. Well, you make a linked list, and in the linked list you have the first element. As we said, linked lists have pointers to the first element, and each and every next element has a pointer to the one after that. So what you do? Well, you have a top element over here, somewhere in the memory. You have a top element. This is the top element. If you have to add an element, you have a pointer which says this is a top. you have to add an element. What you do? Well, link this with the next element you have to add. For example, this was 5 and this was 13. And this top pointer doesn't point here anymore. It starts pointing here. And you do that again and again and again. If you want to remove, well, then you will need a doubly linked list. Because if you want to remove, you want to go back. You have to go over here. You can't go over here if you don't have a pointer to there. So if you want to represent a stack with a list, it will have to be a doubly linked list. Meaning that each time you delete an element, you have to know where to start pointing, where the top is again.
You can just go for each until you reach the end.
Yeah, but that will be slow. You can go for each until you reach the last, until you reach one before the last element, and remember what the previous element was, what its location was, and then delete. But that will be slow. That's if you don't want to use more memory, but that will probably not be the case in your tasks.
That's a violation of the stack data structure to get the bottom of the stack.
Well, if it's not a violation because it will be implemented in the stack itself,
But
in the class stack.
You shouldn't get a reference to the. You shouldn't be able to get a reference to the.
You shouldn't be able to get a reference to the previous element also, but you have it with the doubly linked list.
But you could set it as a private, and this only the stack class will have access to it.
Well, that's exactly what I'm saying. If that for each loop which goes through each and every element will be in a method which is a member of the stack class, and of course we will implement it the way we want to. And if someone wants to delete for each, you do your own for each in the class. Do what you have to do. That's not a violation as long as it's in the class. As long as you don't have a public function, a public method which gives you access to something you shouldn't get access to, you're keeping up with the definition. If you have something public which gives you access to the base of the array, for example, then you're doing it wrong. So, stack class in .NET, well, nothing too special. The stack class uses an array. So that means it will basically resize slow. Of course, it can increase its size. It's not as fast at increasing size as a doubly linked list is. That means that if you want to make your own fast stack, well, you program it yourself using a doubly linked list. So, or you download it. There are a lot of libraries on the internet which give you, for example, stack implemented by linked list, priority queue, and other things that we will talk about now. But you won't be able to use them on your exam because you only paste your source code, and we can't have the source code of any other library you could be using. So when you write your program, write the solutions for the exam, use only .NET, only things which the system has. That's a little stray away from our main subject which we're speaking about. So, what about the stack? Well, same thing, same syntax as the list. You say a stack of some data type. Whether it's int, string, object, my car, or something like that, doesn't matter. Just some data type. And it resizes itself the way it knows. You don't have to resize it manually, because you shouldn't be able to access it manually. And it has push and pop statements. And what does a push do? Well, it takes an element type, the type you used here. For example, you push, if you have a stack of ints, you can push only ints. If you have a stack of strings, you can push only strings. It takes an element to push in, and the pop method, what it does? Well, it pops the last element, it removes it from the top. And some other functionality, peek, what I told you, see what the value of the top element is. Only the value, not pointers, not anything else, only the value. And doesn't remove it, only gives you it. Count, That gives you how many elements you have in the stack. And as we said, count is basically implemented by any data type in C#. Clear clears everything, contains. This could be considered a violation of the stack definition, because you shouldn't have this access, but obviously the creators of C# decided that you should know what elements there are in the stack, but you shouldn't be able to access them. Don't know why they decided it. So it has a toArray method, which, guess what it does? It takes this stack over here and transfers it into an array, each and every element. Correspondingly, the top element comes at first position, the next element comes over here and over here, etc., etc., etc. You can implement this your own way at any time. Trim access, what does trim access do? Well, the stack in C# resizes like a list, like a static list, which uses an array. And trim access, well, trims the same way the list trims, meaning that it removes its excess memory which it got. If it has elements up to here, trim access will remove this part. So that isn't really something you need to know. You just need to know that when you decide that your stack isn't going to grow anymore, you should use trim access so you don't use up more RAM than you need. So, and if there is a possibility that you will need more memory, well, then you don't trim access. So, how do you use push, pop, and peek? Well, very simply, you push something, you give your stack some value, meaning this thing over here means an empty stack, nothing in it. And if you say push and push and push and etc., it will tell you, it will put in the stack some values. Pretty simple. And how do you pop values? Well, you can't. How do you get the values? You can't use a for each. You don't have access to these things. But you can do a while, and while your stack is not empty, and this, I don't think it's necessary to say count larger than 0. I think the stack has a method isEmpty, but we should check that. And if this thing's count is larger than 0, we will say remove the element, and remove the element also returns us the value of that element. So, how does this thing work? We go to our solution explorer, say stack example is a startup project, and open it. Here's our stack: Ivan, Nikolai, Maria, George. And start this thing. Top is George, and the others are Maria, Nikolai, Ivan. So, this actually effectively emptied our stack. How did we say top is George and then print it again? We said peek. Give me only the value. If we say stack.peep here, what will happen?
Infinite loop.
Yes, this will be an infinite loop. Yeah, I said peep. So, if we say peek, this will be an infinite loop, and it won't change anything on our stack. So, what will happen if I say while true, and this thing says pop? Will it be an infinite loop? It won't. It will be something which didn't throw our exception as it should have. Oh, it threw it. Invalid operation exception, or the other so-called operation, which is in the other so-called exception, stack underflow exception. You've all heard of stack overflow. Stack underflow is when you try to pop elements when the stack is empty. Stack overflow is something you don't want to happen in your program. What can cause a stack overflow? Well, stack.push 1, for example. And this will probably, this is not 1, this is a string. This will run, oh, come on, stack.push. Oh yeah, thanks. So if we say stack.push infinitely, and we remove this stuff, stack.push infinitely and start this thing. This thing will fill up our RAM memory. And if we turn on our task manager and say, yeah, we didn't need to do that. It stopped working at some moment. And what's the exception? Out of memory. What happened? Our stack became infinite. And my 6 gigabytes of random access memory ran out, and we got an out of memory exception. An exception we can't catch, by the way. You can't catch out of memory exception. Out of memory exception is something that's outside of your program. So, yeah, you saw how to push and how to pop and how to boost up your program. That's fairly simple stuff.
Yeah.
I'm interested in catching out of memory exception. In some of the programs we are writing, there is a possibility.
In some programs, yes, but out of memory can happen at any given time. Some other application might fill the memory of your computer. It might not be your application. And when the memory of the computer ends, you can't know that happens, and you start to push something, and you get out of memory. You can't control that. You can't save yourself from that. That's normally a problem of not your program, but someone else's. So you shouldn't worry too much about that, at least for the time being. Oh, and by the way, the system which tests your solutions had a bug last time, and it didn't give an out of memory exception when you used more than 16 megabytes. That was the limit. It gave an index out of bounds exception. So I think we'll fix it until then. I found that bug when I was solving one of the problems. I think we'll fix it by the time you get to your next exam, but be wary of it. It's not guaranteed. Watch out for index out of range exception when you don't have any indexes that are out of range. Watch out for that. That could probably mean out of memory, not out of bounds, because the system doesn't actually run out of memory. It gives you some piece of memory in which you should work, and you get an index out of bounds because you leave that memory. Anyway, that isn't very important. How do you check if an expression has the right amount of brackets? You have some brackets, you have other brackets. You have opening brackets and you have closing brackets. Well, this thing can be implemented very easily in a stack. When you get this kind of bracket, you push the index in the stack. When you get another bracket, you pop the last index. So that way you will have the indexes of the brackets, and each time you get an opening bracket like this, you will get a closing bracket also. So actually can be nested. Yeah, extract all sub-expressions. So basically the basic functionality of a stack is to check, for example, the brackets. If you want to get the sub-expressions from these brackets, well, each time we will add this type of bracket, and it's in the index of this type of bracket. You know, this is a string, right? This is a string, and we start looking. Okay, one bracket, so this is opening. We don't care about this, and we say this is at index, for example, 3 or something like that. We go on further. This is at index 4, 5, 6, for example. And further, and we reach the closing bracket. And when we reach a closing bracket, what do? Well, get the index of the last opening bracket, which is 6, and get that substring to this bracket, to the position which we've encountered, our closing bracket. That means 6, 7, 8, 9, to 9th position. This is a sub-expression, and that sub-expression is 2 plus 3. And you pop this thing from the stack and continue on. You reach another opening bracket, same thing happens here, and you reach the last closing bracket, which you saved here. It still is in the stack because you've had only 2 closing brackets and before them 2 opening, right? So you basically destroy these and this one still hangs out in the stack. And when you reach this one, it tells, give me the index of the first one, and you get the entire sub-expression. So, how does this thing work in code? Well, you check if the character you've reached is an opening bracket, save its index in the stack. If it's a closing bracket, take the substring from the top of the stack to where we've reached now, and print that, for example, and pop that bracket, that index, the last index. We don't add the indexes of the closing brackets, only of the opening. Check this thing out yourself, and you will see that. Solution Explorer, matching brackets. How do we match brackets? We have some expression from 0 to the length of the expression. If it's an opening bracket, push it in the stack. If it's a closing bracket, get the index of the matching opening bracket, and then take a substring from the opening bracket to the length, which is our index minus the starting index. The starting index is the opening bracket, and write it to the console, for example. This thing doesn't have error checking, and this thing isn't the project we're looking for. Matching bracket.
There is other way to set it.
Yeah, there are other solutions to this one, but this is a good example how you can use a stack. There are better.
No, I mean for the running project.
Yeah, for running the project, there's another way, saying properties over here on the solution and saying current selection. But I randomly choose from one of these ways. So, of course, there are other ways to solve this task, but this is one of the convenient ways. So, what will happen if we do something like this? Probably nothing. Start this thing, it will still work. A lot of opening brackets, an invalid statement, but we have no error checking for that. So, what will our error checking be? Well, at the end of all these operations, at the end of the for loop, we say if our stack, which is stack, has a count larger than 0, we say that there were too many opening brackets. Too many opening brackets. Because we're still left with some opening brackets which we haven't removed. Start this thing. Here's our message. Too many opening brackets. What will happen if there are too many closing brackets? For example, over here, yeah, we'll get an exception because we'll try to pop something that isn't there. How do we handle that? Well, we say try. We'll say a try over here and catch. And if we catch something, we'll probably have too much closing brackets. Try to do this and catch an exception. I'm too lazy and I won't catch the exception correctly, but you should, because we will have a quality code lecture. And catch and console write line. Too many closing.
Or we can also write one if after the if for the closing bracket.
Yeah, we can write another if statement over here. This thing would work also, but yeah, too many opening brackets. If it gets an underflow exception, you get this kind of error, an exception which is invalid operation exception. It should be stack underflow exception, but I don't know why it isn't. So, no matter. The important thing is, this is one way you can use stacks. There are other ways. When you implement recursion, it actually uses a stack. Your function is stored in a stack, and the first method which will be executed is the last one which you've called. In a recursion, the last thing which you've called will be the first that will be executed, and then the other thing that calls it, and then the other, and the other, and the other. That's why there's a program stack, because it functions in that way. It executes the topmost order. So, queues. Well, queues look like this, sadly. They can look even sadder, but that's another question. So, queues, well, the first guy in, I think this is a guy, it could be wrong. So the first guy in will be the first one that leaves, the first one which finishes his job. So he will leave first. This guy over here will leave second, third, etc. This guy is screwed and will leave last. So, again, we will discuss the static and dynamic representations of a queue. What's important is the queue is a first in, first out. Contrary to the stack, which was first in, last out, this is a first in, first out. It's pretty standard. All elements are inserted at the end. In the stack, they were inserted at the beginning. In the queue, they are inserted at the end, because when you enter a queue, you're last. So, yeah, useful when you imagine where. You can give a queue of orders to something. For example, tell your computer to first download a file, then rename it, then delete it, then do something else. That's a queue. It's a queue of orders. Actually, your programs are a queue of statements, which is ordered in a sometimes strange way. In the past, programs were just a queue of orders because there was no branching, no if-else, no function, no methods, no functions, no classes, no anything. There was goto, which was very damaging, but basically that was a list of things to do. And a list of things to do in a sequence is a queue of orders. And again, can be implemented in several ways, and you will most likely use this queue class, which is in C#. So, this thing has some fixed capacity if it's static. What happens? Well, you have some elements, preferably starting from somewhere. It doesn't have to start from the middle, like in this example. It could, but it doesn't have to. So some array with values in it, and you have a head and you have a tail. Basically, head and tail point where your first and your last element is. And this thing, in this case, is called a circular array or circular queue or whatever, where head and tail can coincide. You can have a situation where head and tail coincide, but that really shouldn't be a word for you. Don't consider these things. Don't consider circular arrays. You should consider only the fact that a queue is this thing where you have an element at the beginning, which is a front or whatever it's called there, front, and an element at the end, which is end or last or something like that. What happens when you add elements? They come at position end plus 1, end plus 1, and then end also goes at end plus 1. So this thing is no longer valid, and there's another element here, etc., etc., etc. When you pop elements, that is when you dequeue them, well, the front goes back. So you have a front over here, and you have some other elements, and the front points to this. When you remove an element, the front starts pointing to the next element, and so on. That's how you implement it basically with an array. When you coincide your head and tail, well, then you have an array which has, then you have a queue which has only one element, because it's both a head and a tail. So, how you do it with the dynamic representation, that is a list? Well, we basically choose the same thing. Again, you make a dynamic list with pointers to each and every element. Not each and every element, I mean, but to the next element. And you have a head pointing to the first one, a tail pointing to the last one. Why do you need both of them? Well, because if you want to add something, you have to add it at the tail. If you want to pop something, you want to pop it from the front, or the head, or whatever it's called. So, the pop command does this. Pop command does delete this element, or don't care about it anymore, and move the head, tell it to point over here. The tail, the push element, or in queue, the in queue method, what does it do? Well, it creates an element over here, gives it some kind of value, for example 7, and gives it a null pointer for next element, and redirects the tail to point at it, and connects this one, connects the last element with the newly created, and then shifts the tail one element after that. Not very intuitive at the beginning when you see it. You have this thing, this thing, this thing, and you have some values, 5, 6, and 7 here, for example. This thing points over here, this thing points over here. And you have an end, or whatever, a tail, and it points over here. You add an element.
It doesn't point to value.
The tail points to a value, this thing points to null. The next element after the last element is null. This thing is null, but when you add a new element, it replaces this null and goes like this. For example, you add 9, and 9 goes over here, and this thing starts pointing to null. And then the tail goes away from here and goes over here and starts pointing at this element. This is how a queue is implemented dynamically. Again, you shouldn't care much about these types of representations. What you should care more about is using the queue class in C#. We're saying these things because you need to know how to implement such data structures, because they're pretty basic. But you won't need to implement them each and every time you use them. That would be overkill. That would be reinventing the wheel. So we're just mentioning them so you can imagine how they're relatively how they look like in memory. And you should use these in the .NET framework, because we're all using C# and .NET to make our lives easier. So this thing uses some kind of array, the same way that stacks use an array, which array is dynamically resized, partially like the list. Again, if you want speed in resizing your stack, and this thing is copy pasted, so this thing should say queue. Yeah, this is an example of queues with a stack. This is not valid, so whatever. We said that. What did we say? We said that queues resize dynamically, just as lists do, and just like stacks do. What you should worry about is when you have a queue in which many people can enter. For example, many people can enter in a short period of time. Then the queue from .NET wouldn't be effective for you, and that's why we said how you can make your own queue. And you can make it, for example, with a linked list, and then adding elements will be very fast. Much faster than adding elements here. Although adding elements here still is relatively fast, but because it doesn't implement linked list, it is still relatively slow. So, yeah?
Why is array type preferred in this case?
Probably to ensure contiguous memory. Meaning that if there is some operation that needs to be done on the queue itself, it will be fast, aside from insertion, deletion, etc. But aside from insertion, deletion, and pushing at the back and queuing, other operations are much faster done on arrays than on lists.
Well, the underlying code is some kind of link with this type. Array.
Well, not. What do you mean underlined code is linked with this type of array?
I mean, it uses array.
Yeah, the queue itself uses an array or a list. Not very sure which of them. Probably an array, and it resizes it its own way. Basically, arrays are faster when you do operations on the elements, because you have indexes. And in lists you don't have indexes. And in some cases it would be preferable to work faster on arrays, or to work faster on the queue than to just traverse through the elements of a list going next, next, next all the time. Because operations on arrays are faster. Operations besides from insert, delete, and add. So, what you need to know, in queue method, sends an element at the end of the queue. The queue method takes the first element from the queue, gives you the value, and removes it. So, in queue and dequeue, here's what we can have with enqueuing and dequeuing. Same thing as the stack, but we'll have the opposite type of output. Meaning that 1 will come first, 2 will come second, 3 will come third, etc., etc., etc. In the stack, if this thing was a stack, they would come in reverse order. One use of the stack is reversing the order of something, if you're too lazy to do it by hand. So, here we go to the queue example, open it, message 1, message 2, message 3. We can do a while, and we can dequeue the elements. We start this thing, message 1, message 2, message 3, 4, etc. If we make this thing a stack, say stack, and this should be a stack also, but I won't name it stack. This is a stack also, and we say push instead of in queue, push again, push, and push, and push. And here we say pop. We compile this thing, and we'll have them in reverse order. This thing you can use in converting numbers from decimal to binary representation. Because when you're converting such numbers, if you divide by 2, you have to put the things in reverse order, right? If you have the number 5, you have the number 4, for example, that's 4 divided by 2, 0, 2 divided by 2, 0, 1 divided by 2, 1. And we get the remainders. So we get 0, 0, 1. But the number is actually 1, 0, 0. So one option is put them in a stack and pop them out when we've finished. And they will come in reverse order. So we saw how a queue works and compared it to a stack. And we're going further. So, something with finding sequences of numbers, and what does this do? Find the index of some number, and index of that number is something. Not pretty sure what it does. First index of a given number p, and n is 3, p is 16. Oh, yeah, and we have a sequence which works in some special way. And what do? I said these things are commands. First command is give me n. Next command is give me n plus 1, then give me 2 times n, then something other, n plus 2, then 2 times n plus 1, and etc, etc, etc. These are a list of commands, and queues are very optimal for lists of commands. This is basically do something and give me the result. So if we enqueue these things, we'll get the result. How do we do it? Well, we make a queue, we start pushing things inside, and we enqueue the last element multiplied by something. Why? Well, because here we have this kind of sequence. First the first element, then the first element plus 1, then the last element multiplied by 2, then the last element summed with 2, and then the last element summed with 1 multiplied by 2. Some kind of sequence in which the sequence is not really specified recursively, because we don't use exactly the previous element. We use some other stuff. And what do? Well, oops, wrong key. What do? Well, we have some index, because each time we're adding the index. We saw n plus 1, something else, then n plus 2, then something else, then n plus 3, etc. We increase some index, and then we do the current element, which is our queue, add to it the current number summed with 1, then the current number multiplied by 2, what we saw over here. The current number, the n, summed with 1, then multiplied by 2. Add these two things. Then, after we get there, get the next number, summed with 2, summed with 1 actually, which is this number, again summed with 1. This is n plus 2 is n plus 1 plus 1. And we get n plus 2. 2 times n is 2 times n plus 1 again. So basically, this is not too complicated. What you have to do is enqueue the things you've added and just that is dequeue the things you've added and do the operations you were requested to do with them. If you try to play around with this code, you will probably understand it better than me just explaining it. How does this thing work? That's not what I meant to do. Sequence, some kind of sequence, which we said will have n elements, and we will want to get the element at index something. We do it until we reach that index. That's why we increase our index. Then, if we reach our index which we wanted, we just output what we've dequeued. Else, we continue enqueuing stuff which we need to use to calculate. Start this thing. Yeah, and this thing was preset to... Why is this thing preset? If we compile it, not pretty sure. Where's... Oh, that's n equals 3 and p equals 16. Oh yeah, and it isn't a read line, it's a write line. So, again, what we got here, we have some initial number, and we do two operations on that number. And then we just have to get the last of the two operations and do the operations again, and again, and again, and again, until we reach the number at some index. This might be a little complicated as an example. What you need to remember about queues is that they can be used to gather commands, gather a sequence of commands which need to be executed. Here you have that exact thing, a sequence of commands. Sequence of commands. First command is give me n, then give me n plus 1, which is calculated on the base of something, etc., etc., etc. For example, another idea is you have to download files from the internet, but you can't download files in any order. You have to download them in a specific order. Well, that's a queue. Do this thing first, do this thing second, etc., etc. Or the idea with the quest. So, which the other people didn't hear because they didn't see the video. What's a quest? Well, do something. Do something. When you do that, you get the order to do the next thing, the next thing, then the thing after that, and so on. Okay, so we saw some example of queuing in queuing orders. What if the orders are somehow with larger priority? So, for example, you have the task to write your homework, but you also have the task to go and drink with somebody, and these tasks come at some random order. Perhaps, for example, someone said, "Oh, Joe, let's go and drink," and then someone else said, "Oh, but you have to write your homework," and then someone else said, "But you have to pay your bills." Well, what do you do then? You do the most important thing first, unless you're lazy and just go drinking. Do the most important thing first. And what kind of data type do we use? Well, we call it a priority queue. For example, how can we make a program that does these things? You have a program in which you input things you have to do and some value, some number, which indicates how important they are. Then you make a class of these things, a class which has task name and task priority, for example. And then you add these things to a so-called priority queue. A priority queue, when you enqueue something in it, it finds its way to the most valuable location, meaning a priority queue will always give you the thing with the highest priority. For example, if you say that the highest priority is the task with the largest task importance, it will always give you the task with the largest task importance. No matter, it doesn't matter in what order you will give them. you might insert 10 tasks, and the 5th task will be with highest priority. And when you say, get me the first task, it will get you actually the 5th, because it has the highest priority.
Does that mean that the things in the priority queue are sorted by
Yes.
priority?
Things in the priority queue are sorted by priority, or implemented in some other way with some other constructs. But yeah, basically you can imagine that things in the priority queue are sorted by their priority. It's not exactly that case. It's something like that using some other abstract data types, but we won't fall into discussion of them because it will get too complicated. So this thing is the most efficient when you have things to do or values to consider, and you want to get, for example, the smallest or the highest. That's what the priority queue understands. So it has these basic operations like in queue and dequeue. And the bad thing is that the priority queue is not built in. But it's built in this thing. This thing is called power collections. Okay, so let's be a little more clear. Why is there no built-in priority queue in .NET? Well, because we said that abstract data types define what should happen. So the priority queues defines that, for example, the smallest element should be dequeued first, or the largest, or whatever you tell it to be. But there are several ways to do that. One way is to keep a sorted array in which, of course, the first element will be the smallest or the largest. Another option is to keep an abstract data type called a heap. A heap is something. So, I accidentally stopped the recording. Things like this happen. Today is not my recording day. So, what I was speaking was that you can implement a priority queue in a few ways. One way, an array which you sort each and every time you add an element. You understand that that's not very fast. It's fast when you want to access the highest priority element, but it's not fast at it's not fast from the point of view which says when you have to add 1,000 elements, sort the array every time. It's not very quick. There's another data type, abstract data type, of course, which is called a heap. What's a heap? Well, a top node, something like a tree. A top node with some number in it. For example, this is 15. And depending on the priority you use, the elements below it can be smaller or larger. So this one will probably be smaller. If we're looking for if we're creating a priority queue which uses top priority things, then we'll need the thing at the top to have the highest priority, the highest number for priority. So the thing below it will have a priority of 7. The other thing will have a priority of 9, for example. This is not a binary tree. This is a heap. What is characteristic of a heap is that it has some elements. The top element is always the highest, the largest number. The left element is some number smaller than the top, for example 7. The right element is something larger than the left and smaller than the top. So here is, for example, 11. This is an idea of a heap.
If you add, for example, 6, what is that?
6 is going to come over here because it's smaller than 7. These over here are between 0 and 15. These over here are between 0 and 7. These over here, at this part, are between 7 and 11 and 15. Basically something like that. Explaining this stuff will probably take some time. how to explain it quickly. Well, basically, when you add an element, you start going down. And when you go down, for example, you want to add 8. You want to add 8, what happens? 15. Okay, is it larger or smaller? Well, in this case, 15 is larger than 8, so we have to go down. Is 8 larger than 7? Okay, is it smaller than 11? Okay, so goes over here. Well, I think I lied to you. I think I just lied to you.
It's some kind of binary search.
It's not exactly a binary search. If it was a binary search, if it was exactly binary search, 15 would be smaller than 11. Smaller than the thing over here.
Right sub 3 should be bigger than the root.
Yeah. The right sub tree in a binary search tree is always bigger than the root. If this is 5, this is 10, and this is always smaller, for example 3. But in the heap, the root is always the largest. And that's how you implement a priority queue actually. Why? Well, because if you want to implement a priority queue, you want something with top priority at the root, so you can take it right away. So you have the thing with the highest priority, the highest or the lowest number, whichever you decide, at the top. Then you have two other numbers, one bigger and one smaller. For example, this is with the same example of something else, 6, and this is 13. So basically, to the right of this, you have anything smaller than 15, smaller than I'm lying to you. If you have something at the top, everything below it should be smaller than it. And I'm probably going to lie to you about the order. If you have something smaller than 6, it will be here, 5. If you no, 5 is not a good example. If you have smaller than 6, it will be here. If you have larger than 6, larger than 4, but smaller than 6, it will be here. 5 will be here. If you have something between 6 and 13, it will be here. For example, 12.
7 and 13. 7 and 15. So because
In the, yeah, bigger.
separated in the middle.
Not, it's not separated in the middle, and it matters on effectiveness. It's separated from. This is the lower part of the range. This is the lower part of the range, 6, and the higher part of the range is 15 for this entire thing, for this entire subtree. For this subtree, it's separated by 6 and 13. So 6 and 13. This is the range for this subtree. The range for this subtree over here is 13 to 15. So in this subtree, what value can we have only? If we're talking about integers, 14. 14 should be here. This is important because this is how you balance that heap. Now the requirement for the heap is that the requirement for the heap is basically this thing. I can't formulate it mathematically, but you saw the example. Now everything below 15 is smaller than it. The left one is between 0 and 15. The right one is between the left one and 15.
The
And
one is between 0 and how? It's not 15 to sure. It's between 0 and how? And 8 maybe? 8.
Not.
You can't have 14 there because it's bigger than 13.
Oh yeah, I lied to you. I'm going to keep lying to you today. If you add 14, yeah, it will come over here. 14 will be over here, and 13 will be below it.
Okay, for example, you have only 15 and you are adding 8. Where it go?
You have 15. Doesn't matter actually.
No, it goes also on the left.
It goes on the left, or what? Okay, if we're going to use right and left, it goes on the left. It checks if there's a left one. If there's no left one, it goes on the left. So this is 8. Okay, let's experiment. That's what you do when you're at the exam and you start wondering how to do it. You have to have smaller things below each one of them. So, add another number. For example, we saw what happens with smaller than 8. We want to add 12. What happens when we add 12? Has to be right, I think. Right. Or should be over here. Let's check. Okay, add another number. Say 13. So when we add 13, what do we do? Should go below and should go. Should.
I think we should not have
You put a number, you have an array, right? And you put it in the last place, the new number. Then you swap the first number with the last number,
Yeah.
and then you will just.
Yeah. And if you have a tree, you do it with the rightmost node, I think. Yeah, thanks. Okay. Another. What I tried to do here is do a binary search positioning of numbers on something which is not a binary tree. What you do in a heap, thanks to the colleague who mentioned it and reminded me, in a heap you have the top thing and you have the bottom things. You have all the leaves. For example, in this case, if we add a number, you start from the bottom. This is the bottom over here. Start from the bottom and try to go up. In the heap, things work in the reverse way in which they work in the binary tree. So in the heap, you start from the bottom and try to swim up. So in this case, 8, well, you try to swim up from below and you see 15 and you connect it. So this is 8. Again, if you're always trying to add, to try to swim to, you're always trying to go up from the rightmost node, from the rightmost leaf, etc. So if you're adding something again, for example, you're adding 7. If you add 7, I think it will be okay. Not pretty sure. If you're adding 7, it should come over here. If you're adding something else, it should come beneath 7, I think. Okay, I'm going to lie to you a lot of times today, so I'll just check it in a moment. The idea is that you have this heap data structure, and you should check it because I'll lie to you another 100 times because I'm not sure how it's implemented, and I'll check it in a moment. Check that heap structure. What that structure is good at is giving you the highest priority element and changing the highest priority element. That is removing the element at the top. How is it fast at removing the element at the top? Well, when you have a tree, when you have a top element connected to some other elements at the bottom, connected to some other elements, etc. What you do when you remove it is you merge these two trees. And when you merge these two trees, that's a fast operation, and it takes binary logarithm from the number of nodes, I think. Not pretty sure. So the idea is that removing the top element in this type of data structure is quick. And that's why a lot of implementations of priority queue use it. Whereas removing the top element in a binary tree is also quick, but the top element is not the highest priority element. And that's why the heap is more commonly used in making priority queues. Because if you have a binary tree, removing the top element is quick, but getting the highest priority element means reaching this place, going here. And this is binary logarithm of the number of the height of the tree, and meaning the number of elements if you have an array. If you have 1,000 numbers, a binary search will complete in 32 steps exactly of a tree. If you have a heap, searching the highest element will take 0 time. Constant time, meaning it will just give you this one. That's the difference between a heap and a binary tree, and it's a little hardcore writing it. Well, not that hardcore, but It's not very simple. As you see, I'm starting to confuse my own self. So I'll check it in a moment how you do that. And by then, I hope you've reached some ideas how to build a heap by looking in the internet. Because when you get to the exam, you will probably not remember how to write a heap. And you search it on the net if you need it, and you implement your own heap and your own priority queue. So what's the priority queue actually? Well, the priority queue's operation dequeue gets the topmost element. Dequeue gets this and merges these two trees, merges this with this. And queue throws an element into the bottom of the heap, starting, if this is the heap, throws the element at the bottom of the heap. I think rightmost, I'm not sure, the rightmost leaf. And that element tries to go up and find its place in the heap. Again, these things should be checked. I'm not very sure how it's implemented. That's a way to create a priority queue, and that priority queue works relatively fast. It works faster. The other way to create a priority queue is just ordered back. Yeah, that's the way you create a priority queue. The normal way in C#, obviously, in which you create a priority queue. The dumb way to create a priority queue, if you're in a hurry and you don't want to write complex algorithms, is make an array, and the dequeue method does what? Well, searches for the element with highest priority, for example, over here. These are some elements, and these are some elements over here. A priority queue, the operation dequeue finds this element over here and extracts it and reorders the array. That's one option. The other option is to sort it every time, which again is something very slow.
But
Depends on the,
then it's not good.
But how do you find the smallest element? How do you know that
Yeah.
it is the smallest?
you
When
find
you are binary sorting, just you're
Again-
searching for this.
But how do you know what to search for? You don't know the number.
You
that search
know what you are adding. Then you know what
the
is
problem is
value of
the problem is that it still takes time. Yes, but getting the first element of the array or the heap doesn't take time. It takes a constant amount of time. And searching for an element takes an amount of time depending on the number of elements you have in the heap.
Again, getting the element doesn't matter which, even in sorted array, it doesn't take time.
It takes a constant amount of time. A processor instruction.
It's the same as in the heap case, because you are just taking the index of 0. In the heap, let's say,
Yes.
the top one is the index of 0.
Yes.
It takes same time. Adding an element,
Adding an element means sorting. Yes,
so
if you use a sorted array, but
then
that's
if you are sorting in heap, then again you are taking more operation.
but in the heap the it's not a sort operation actually. It's a swim up operation which takes really little time. I'm not sure of the logarithm of time, even in some cases shorter. And sorting an array always takes longer time. It takes n log n, which is n multiplied by that which heap does.
N times slower.
N times slower, yeah. Actually, that's n times slower. So, what I tried to think of an algorithm to build a few minutes ago was that thing called ordered back in C#, obviously. So that ordered back should be my heap, which I tried to build a few minutes ago. So this ordered back, yeah, it has an add, and it has a get first, and a remove first. This thing is, I don't know why it's called an ordered back. I have no logical explanation why this thing is called an ordered back when in all other programming concepts it's called a heap. But this ordered back is something that you now know you can use instead of implement. So that ordered back does these things I tried to do. It can add elements, and it can get the first element, and the first element will always be the largest. or the one that's ordered by the ordering function. So yeah, it's not a priority queue, it's an ordered back, and I'm not even sure why they create a priority queue class where there's an ordered back class. Whatever.
The
So
ordered back isn't part of the it's from the power collections.
you certain?
Yeah.
Okay.
It's not integrated in the
Then we'll probably have to consider the idea whether to include the power collections in the exam. But yeah, I know it would be nice, but you will probably be
Is there a class called Heap or something like that?
no. Basically, the heap is actually the priority queue. So
Because
okay.
here in Wikipedia there are different types. I mean, there is some max heap, there is priority queue.
What you're looking for is either a max heap or if there's a priority queue heap specific, use that. But if there isn't, use a max heap or use the power collections. We should yeah.
Can we get the source code from the power collections?
Yeah, you can copy paste.
Well,
Well, that's some kind of solution to the problem. Yeah. On the other hand, you can always use some other third-party code, not necessarily the power collections. Okay, so what you have to remember here is the priority queue is an abstract data type which gives you the highest element or the lowest element, depending on what function of comparison you give it, what method of comparison, and that you can find some priority queues in the power collections, but you should try to implement your own, and I'll try to give you some hints on how to do it after I Google it too, because I've forgotten it also. So basically that ordered back from the power collections should do what my imaginary heap, which I couldn't complete, should have done. So some kind of generic type which implements I-comparable. Why? Because you need to compare the elements. In every data structure in which you have to have some type of ordering, you need I-comparable. I-comparable, integers are I-comparable, strings are I-comparable, and a lot of other things in which you can write this sign less than, or more than, or equals, are I-comparable. So yeah, that equals isn't 1, but it's 2 equals. Everywhere where you can write these comparison operators, that thing implements I-comparable. And yeah, you don't need to use the ordered back. You can write your own. And I advise you to do it, because it's some sort of exercise. Adding and removing, as we said, in a priority queue, should be, so depending on your implementation, but should be with this speed. Logarithm of n, which means if you have 1000 elements, adding an element should take maximum 32 operations, not more. Because binary logarithm of 1000 is 34, even 31. So, what you should do, you should get the element that fulfills some condition. Whether it's maximum number, whether it's minimal number or something else, number with minimal remainder when dividing by 7, for example, you might need something like that. You return the element that best satisfies that condition. So,
Actually, ordered back is some kind of tree.
well, the heap is also a kind of tree. Everything in which you have nodes connected with each other, which don't have cycles, meaning that you can get from one place to another place. You can get from here to here in only one route, from here to here. This is a tree.
But then also in ordered back case you have more than 2 rows.
More than 2
Yes.
children.
Yes.
Possibly. Again, it depends on the implementation. Pretty much depends on the implementation. And ordered back isn't actually some theoretical data type, whereas heap is a theoretical data type. And for heap, as a theoretical data type, it is known that the top element is the largest. For the ordered bag, well, I can always create my own data type, which is called Gauch's bag. And it can implement some other quality. What you need to remember is that a heap gives you the maximal satisfying element. So maximal satisfying element for some condition. How you implement it? Well, it's rather complicated. If you have to do it on the exam and you haven't done it at all, I suggest you just use an array and search each time in it, or sort it. If you know that you have to search a lot of times and add a little amount of times, you sort your array and search in it. If you don't, if you have to add a lot of times and search little times, then you just create the array and search every time. If you have to do both of the things a lot of times, well, then you have to do that. Then you have to use a heap. Yeah, then you're screwed. So, a priority queue, a live demo of a priority queue, which will probably have some power collections included. Yeah, power collections DLL. So yeah, this is including power collections in your project. You get the power collections, you get their DLL. I suppose they have source code somewhere. And if you get that source code, you can copy paste it in your code and it will probably work. They should be generic and they should be loose coupled, which we'll discuss in later lessons. They should be written in such a way that if you copy paste them if you copy paste the class, it will work. Not pretty sure, but that's a good.
They are using kludges in the one I found.
That shouldn't be much of a problem.
Then you have to delete all the kludges.
Well, yeah, you could delete some. Yeah, they should be written in a way in a copy paste friendly way. That's one requirement of of well structured classes, but we'll talk about that later. So, some priority queue. What does a priority queue look like? Well, some ordered bag. What does an ordered bag look like? It's over here. Yeah, copy paste this from here to here probably, and some regions and some other stuff. Okay, so they're not that copy paste friendly. That ordered bag does something like my imaginary heap, which I drew a few moments ago, which I'm not sure how to create, or not sure, and in these 5 minutes I tried to explain it. So priority queue uses this ordered bag, and this ordered bag, what do you know of it? Well, we can get its first element, we can remove its first element, and we can add elements. And this thing works fast, and this thing you can use, but it's still better to learn how to create it yourself, even if you do it just once or twice. You could be in a situation where you drastically need that, so learn it. Find code over the internet. I'll try during the exercises to create one of these. So, I'll try to do it, and I think it's worked for less than half an hour, creating such a heap, if you know how to do it. So, what do we have in our main project file? Well, we have some priority queue of people, of persons, in which we say in queue some people, some names, and this thing after them is the value. This is their priority, because we've implemented our priority queue in that way. And then we say the queue are people, and the thing which is people or person, as we said, implements iComparable, as well as int which compares iComparable, which implements iComparable. Our person also has to implement iComparable. This column here says implements this thing, implements methods from this thing. We'll talk about these columns later, more in depth. So, this ordered bag has to know how to sort our persons, how to compare a person to another person, and we tell it how. We implement the method compare to. and compare2 says return the age of this person compared to the age of the other person. Compare2 is a method which int implements, so we can call it. So we compare this int age to that int, the other age. And then our ordered back will know how to sort these people. So when we start this thing, we'll see that that guy, small Goshku, is 9 years old. This one is 11, 15. This is their priority. If we want to sort them in another way, we'll change the compare2. We'll say other dot age dot compare to this dot age. And yeah, come on, build. And we start this thing, and we have Grandma Mara at 70, and I don't know how to translate by in English, but yeah, by one, Makivan or something like that, as 65, and etc. So this compare2 function, the first thing which you put is going to be the smaller, and the larger thing is the next thing. The parameter is the larger thing, the way you want to sort them. If you want if you want them in ascending order, you want the opposite of this which I've written here. But that's something you try out. You won't be able to remember them, so you try the first way. If it sorts them backwards, well, you just have to change their places. So basically that's a priority queue. That's how it works, at least. How you implement it, well, that's a problem. That's a 30-minute problem, basically. And try it and learn it because it's valuable. And when you start working in Telerik one day, you won't need to learn it, but for the exam you should know it. Okay, so what did we talk about today? This is also for the people that couldn't hear me during the first video, which doesn't have any sound. Abstract data types. Some kind of definition of some structure with some functions. How it looks like in memory is not that important. It's important what it does and how fast it does it, and what amount of memory it uses. Personal variations like implementation, like whether I should sort my array which keeps my heap, or whether I should use another representation for it, are details. What's important is what it gives you and how fast it works. And that's how you compare them. A heap is better than another heap if it works faster than it. An ordered back is better than a heap, for example, if it takes less space. Yeah, depending on your case, if you want to take less space, if you want to take more space, etc., etc., etc. Abstract data types are a very large concept, and for now you should learn only these. We'll talk about other ones later. Stacks, lists, queues. We'll talk about trees in the next lecture, and we'll talk about binary trees and etc. and how to program them. The priority queue, well, it's a good idea to check it out. To check out how to create a priority queue or a heap. It's the same thing. Or an ordered bag. Well, yeah, or a douchebag. So, learn how to create that thing. It will be useful for you in all cases. Okay, enough of my jabbering. Any questions besides how to make a heap? Because obviously I need to check it too. Okay, no questions yet. So we're finished for today, and now think about what I'll do with the first video. And we end this stuff. Where are we?